usually, when you look inside a machine, you expect to see exactly how it works, you know?
Right, yeah. Like,
Yeah.
it should be obvious.
Exactly. Like a broken bone shows up as this jagged white line on an X-ray.
Hmm.
Or, I don't know, a blown gasket in an engine is just sitting right there, smoking.
You can just point to it and say, there's the problem.
Right. But when we look inside the massive, like, billion-parameter brain of an artificial intelligence, the X-ray is fundamentally broken.
Yeah, it really is.
We are looking at a diagnostic landscape that is entirely murky.
It is the absolute definition of muddy waters. I mean,
Yeah.
you've got these incredibly complex neural networks, right?
Uh-huh.
And trying to trace a single, quote-unquote, thought through them is less like reading a straightforward X-ray and much more like trying to map the currents of the ocean floor in the pitch dark.
That is such a good way to put it, and that's exactly why we are so glad you're joining us today for this deep dive.
Always glad to be here.
Because we are diving into a surprisingly profound question that gets right to the heart of that murky ocean. We're asking, do AI agents actually think deeper when they're forced to plan?
Which is a huge question right now.
It really is. So we are unpacking this fascinating foundational paper. It's titled, Do Agents Think Deeper? A Mechanistic Investigation of Layer-Wise Dynamics in Sequential Planning.
It's a mouthful, but it's brilliant.
Yeah, so, okay, let's unpack this. The whole premise revolves around the architecture of large language models.
Right.
We know these models are massive. I mean, they're built by stacking dozens, sometimes hundreds, of neural layers on top of each other.
Yeah, just layer after layer of math.
Exactly. But here's the paradox that just, it totally blew my mind. Earlier studies show that when you ask an AI a simple question, it doesn't actually use most of those deep layers.
Exactly. It just kind of bypasses them. And the reason this matters to you, the listener, is actually very practical.
Oh, totally.
Think about the tools you're using right now. If you're relying on an AI to act as an agent, to plan a marketing strategy or maybe write and debug a software program.
Which people do every single day now.
Exactly. You need to understand the nature of that tool. Is it truly performing deep hierarchical reasoning?
Right.
Or is it just doing this shallow, highly sophisticated word association across a massive, mostly redundant architecture?
Yeah, because the answer completely changes how much we can trust these systems to act autonomously.
Exactly. It changes everything.
So let's dive into this depth paradox, because for the longest time, the golden rule in AI development was incredibly simple. Just build a bigger model, get a smarter AI.
Right. That was the prevailing wisdom for years. It was heavily driven by scaling laws.
More is more.
Exactly. The underlying math essentially suggested that model depth, literally adding more computational layers to the network, was what allowed the AI to take a massive abstract goal and decompose it into a structured plan.
Okay.
The assumption was just that the deeper you go, the more complex the feature construction gets.
Right, like a taller ladder lets you reach higher. But then the mechanistic interpretability researchers, the folks who were actually trying to build that AI X-ray machine we talked about.
Yeah, the people doing the hard diagnostic work.
Right, they started looking under the hood. And what they found in these earlier studies sounded incredibly damning.
Yeah, they found one famous study called the unreasonable ineffectiveness of deeper layers.
Ouch. Unreasonable ineffectiveness. I mean, that sounds like a terrible performance review.
It really does. It's a brutal phrase, but, well, the data totally backed it up at the time.
How so?
Well, when researchers looked at standard single-turn tasks, like just asking an AI to summarize a paragraph or, answer a trivia question.
Just a basic prompt.
Right. They found that the actual semantic concept-forming part was saturating very early in the network.
Saturating early. Meaning what, exactly?
Meaning the AI would figure out its answer in the first 20% of its layers.
Oh, wow.
Yeah, and the rest of the network was just spreading redundant operations around. It wasn't really adding new thoughts.
Okay, so to put this in human terms, it's like a company building a massive 100-story corporate skyscraper because they think they need all this space for complex logistics.
Okay, I like this analogy.
But then you X-ray the building during the workday, and you realize the actual work stops on floor 50.
Yep.
The top 50 floors are just like people passing empty folders back and forth just to look busy.
That is a remarkably accurate way to visualize those early findings. I mean, for static, single prompt tasks, half the skyscraper was essentially redundant.
But wait, is it actually fair to judge the entire architecture of an AI based on a single prompt?
That is the million-dollar question.
Because if I ask you right now, what's the capital of France?
Yeah.
You don't fire up your full critical reasoning faculties.
No, I just retrieve Paris.
Right. You just hit Paris. You don't need to x-ray your whole brain for that. So what happens when the AI actually has to do a real multi-step job?
And that is the exact blind spot this new paper targets.
Okay.
The researchers realized that testing an AI with isolated static questions naturally strips away all the sequential complexity.
Because it's too easy.
Oh, exactly. It's an artificial environment. They hypothesized that if you put the model in a dynamic environment, one that forces it to use tools, get feedback from its environment, and plan over an extended trajectory,
A real workflow.
right, that complexity would force a completely different adaptive allocation of its depth.
Meaning you can't just ask the AI for a trivia fact. You have to force it to go to work.
Yes.
So the researchers built these intense multi-turn trajectories across 3 really demanding domains.
Which were deep research, code generation, and tabular processing.
Right. And we're talking about tasks where the AI has to search for information, read it, realize it's the wrong information, go search again, write code, run the code, hit an error, and debug the error.
Precisely. It is an iterative compounding process. It builds on itself.
But to actually see what the AI was doing inside its brain during all of this, they use a technique called layer skipping interventions.
Yes, very clever methodology.
And I want to make sure I'm wrapping my head around the mechanics of this, because it sounds like they are essentially performing targeted power outages inside the AI while it's thinking.
That's a really great way to frame it, actually.
Really?
Yeah. Mechanistically, as an AI processes a token, which is a piece of a word, it passes a massive mathematical vector up through its layers.
Okay, passing the math up the chain.
Right. Each layer tweaks that vector, adding computations, and passes it to the next. What layer skipping does is intervene in that flow.
So they just interrupt it.
Exactly.
Huh.
If we want to test layer 20, we temporarily bypass it. We take the output from layer 19 and feed it directly into layer 21.
Oh, wow.
Yeah, completely nullifying whatever work layer 20 was supposed to do.
So going back to our skyscraper, you just cut the power to floor 20,
Mm-hmm.
and then you watch to see if the people on floor 80 panic.
Yes, though we measure that panic using a metric called the future effect.
Future effect. Okay.
After we cut the power to that specific layer, we measure the relative change in the computational states of all the downstream layers.
So looking at how much things change later on.
Exactly. If we skip layer 20 and layer 80's internal state collapses or just wildly changes, it proves that layer 80 critically, causally depended on the specific features generated by layer 20.
It proves floor 80 physically cannot do its job without the paperwork from floor 20.
Exactly. And when they mapped these causal dependencies across these complex multi-turn tasks, the results were a massive aha moment for the field.
Because the AI's behavior completely changes over time, right?
Night and day difference.
Let's walk through what they saw. In turn 1, the very first interaction.
So in turn 1, the dependency maps look exactly like those old quote-unquote inefficient studies.
Just a simple prompt.
Right. The causal dependencies are highly sparse and localized. The deep layers don't really matter. The AI is only using the bottom floors of the skyscraper.
But then the AI gets to work, it writes some code, gets an error, tries to fix it. It gets to like turn 4, turn 5. What happens to the map then?
The maps literally light up. The researchers observed a phenomenon they call progressive layer mobilization.
Progressive layer mobilization. That sounds intense.
It is. Those intermediate and deep layers that were completely dormant in turn 1 suddenly exhibit a pronounced surge in influence.
So they wake up.
Exactly. The causal dependencies become significantly denser, extending deep, deep into the network.
Why, though?
Right.
Like, mechanistically, what is triggering the top 50 floors to suddenly wake up and start working on turn 5?
It really comes down to the compounding burden of context maintenance.
Context maintenance.
Yeah. In turn 1, the model is just generating a fresh response to your prompt. It's easy. But by turn 5, it's carrying a massive cognitive load.
Right, it has history now.
Exactly. It has to retain the original goal from turn 1, analyze the code it generated in turn 2, process the error message it received in turn 3, and formulate a fix for turn 4.
Oh man, it has to hold all that in its head at the exact same time.
Exactly. As the planning horizon expands and that context accumulates, the model can no longer rely on shallow, localized feature construction.
So the bottom floors are just too busy.
Right. The early layers are busy just maintaining the historical context, which means the later, deeper computations become absolutely indispensable.
Because they have to synthesize all that information and figure out the next actual step.
You got it. The sequential complexity forces the model to unlock those deeper computational paths.
Okay, so the skyscraper is finally using all 100 floors because the logistics of the problem actually demand it.
Precisely.
That makes sense. But here's where my mind gets a little blown.
Oh, yeah.
It's not just that the deeper layers are waking up. It's how they are operating.
Yeah.
The researchers found that the AI isn't just smoothly building an idea. It's actually actively arguing with itself.
Yes, and to measure that, they moved from causal tracing to analyzing the geometric alignment of the internal updates.
Geometric alignment.
Right. They used a concept called residual cosine similarity.
Okay, I want to try an analogy here to see if I'm understanding the math on this. Because the AI is on a trajectory, right? A path through mathematical space.
Yes, a vector trajectory.
So in turn one, the AI is packing a suitcase for a trip. It's
Yeah.
tossing things in shirts, pants, shoes. It's just adding to the pile and moving further down its current path.
Right.
The researchers call this feature amplification.
That's a solid baseline. Mechanistically, the new computation from a layer perfectly aligns with the overall residual direction the trajectory of the model is already on.
So it's just building momentum.
Exactly. It's stepping on the gas pedal, reinforcing the existing semantic features.
But by turn 5, the trip is changed entirely.
Things went wrong.
Exactly. It's no longer a ski trip, it's a beach vacation now. So the AI isn't just adding to the suitcase anymore.
It has to swap things out.
Right.
Yeah.
It's furiously unpacking, yanking out winter coats to swap in swimsuits. It's actively correcting itself.
And that swapping is where the trajectory analogy comes in. It's not just stepping on the gas anymore, it's yanking the steering wheel in the opposite direction.
Oh, okay.
What the residual cosine similarity data shows is a stark shift. Early turns are dominated by stable, positive alignment packing the suitcase.
Just normal amplification.
Right. But as the multi-turn state gets complex, those alignment profiles become highly oscillatory.
Oscillatory, meaning the internal states are just bouncing back and forth violently.
Essentially, yes.
Wait, if the AI is constantly unpacking and repacking its context like that, isn't that horribly inefficient? I mean, why wouldn't we just design an AI that gets it right the first time without having to oscillate?
Well, it looks inefficient on the surface, but it's actually vital recalibration.
Recalibration.
Yeah. The researchers found high-frequency phase changes in the intermediate and depth layers. The model is toggling rapidly between amplification stepping on the gas and correction yanking the wheel.
So it's fighting itself.
The updates begin to directly oppose the residual direction, indicating the suppression of previously accumulated features.
Wow.
It has to oscillate because the environment is dynamic.
Yeah.
An error message completely changes the context. If it didn't suppress the old assumptions, it would just keep generating the same broken code.
So it's not a flaw in the system? The oscillation is the AI actively thinking and reacting.
Exactly. It proves that agentic reasoning is not just a smooth, monotonic A to B to C transformation.
It's messy.
Very. The AI is experiencing massive structural cognitive load. It has to repeatedly inject new information, suppress outdated context, and reorient its goals just to maintain a coherent state over a long trajectory.
Okay, we've established that agents use deeper layers for complex tasks, and they use them to constantly correct and steer their internal state.
Yep, that's the core of it.
But here is where the paper throws another massive curveball.
Oh, the gap.
Yes, the researchers found that even when the AI figures out what it wants to say, it doesn't just spit out the answer. There is this massive delay inside the network.
They call it the construction refinement gap.
Yeah, and this is wild to me.
It is one of the most fascinating findings in the paper. They wanted to quantify effective depth.
Effective depth, okay.
Basically, exactly when the internal representations reach semantic maturity versus when the final output actually stabilizes.
So when it knows the answer versus when it says it.
Exactly. And to do this, they use a brilliant mechanistic tool called the logit lens.
Let's break down the logit lens, because this sounds like literal mind reading.
Right.
How are they peeking at the AI's intermediate thoughts?
Well, the AI's thoughts inside the intermediate layers are just dense, abstract mathematical vectors. They aren't words yet.
It's just raw numbers.
Right. What the logit lens does is take that intermediate vector, say, right after layer 40, and prematurely project it through the model's final vocabulary matrix.
So it forces the AI to translate its raw, half-baked math into English vocabulary way earlier than it normally would.
Precisely. It's like taking a baker's mixing bowl halfway through a recipe and chemically analyzing the batter to prove that they are, in fact, making a chocolate cake.
Even though it hasn't been in the oven yet.
Exactly. By using the logit lens, the researchers could pinpoint exactly which layer finished the active feature reorientation, the point where the AI essentially finalized its core semantic direction.
And what they found is that this semantic direction forms surprisingly early.
Very early.
So, if the AI already knows it's baking a chocolate cake by floor 40 of our skyscraper, why does it keep sending the batter all the way up to floor 100?
Right, why not just output it?
Yeah, is it just over-engineering its response?
It looks like over-engineering, but it's actually the refinement part of the construction refinement gap.
Okay.
The deep layers aren't building new concepts anymore. They are dedicated to fine-grained calibration. They are stabilizing the final output probabilities.
And why does it take so much effort?
Because in an agentic workflow, that is non-negotiable.
What do you mean? Why is calibration so important?
Well, think about writing code to query a database.
Yeah,
The AI might know the logic of the query by layer 40.
it knows what it wants to ask.
Right. But if it outputs a single misplaced comma or uses the wrong syntax bracket, the tool crashes and the whole multi-turn trajectory fails.
Oh, the syntax has to be perfect.
Yes. The deep layers are desperately needed to massage the probabilities of every single token so that the final output is structurally and syntactically flawless.
This is why, when you ask an AI to write a complex Python script, you sometimes see it pause for a second.
Exactly.
It already knows the core logic it wants to use, but those deeper layers are agonizing over the exact syntax so the code actually compiles.
Getting the idea is only half the battle.
Right, proofreading it so the tool doesn't break takes up the rest of the brain power.
Exactly. But here is the architectural twist that the researchers uncovered. Not all models handle this gap the same way.
Oh, really?
Yeah, the paper compared different model families, specifically contrasting dense-like models, such as a Quen and Minimax, with shared sparse expert architectures, like GLM.
Let's unpack the mechanics there, because dense versus sparse is a huge distinction in how these models operate.
It is massive. In a dense model, every single parameter, every neuron is activated for every single word it processes.
So everything turns on all at once.
Right. It's a massive centralized filter. The researchers found that dense models, like Quen and Minimax, show a very pronounced construction refinement gap.
Right, the data showed they finished their active feature reorientation. They finalized their core concept, sometimes around 40% of the way through their layers.
Which is super early.
Yeah.
Which means they require almost the entire rest of the network, up to 98% of their total depth, just to progressively refine and stabilize those already formed representations before outputting them.
Wow. So 60% of the skyscraper is purely dedicated to proofreading syntax.
Basically, yeah.
They figure out the answer by lunch and spend the entire afternoon agonizing over the commas.
That's a very apt way to describe it. But then you look at GLM, which uses a shared sparse expert architecture.
And how does a sparse model mechanically differ from a dense one?
Well, instead of activating everything all at once, a sparse model contains a router network.
A router network.
Yeah. When a token comes in, the router dynamically sends it only to specific, highly specialized subnetworks, or experts.
Oh, I see.
It saves immense cognitive load.
So instead of hiring one giant general contractor to build the whole house where everyone has to sign off on everything, you have a project manager routing the electrical work only to the electricians and the plumbing only to the plumbers.
Exactly. Perfect analogy. And because of this routing, GLM's depth allocation is highly domain dependent. It changes based on the specific job it's doing.
And so it adapts.
Right. In highly specialized tasks, like code generation, GLM routes to its coding experts, and it actually builds features deep into the network up to 74% of its depth.
Wow, so active concept construction is happening much, much later.
Yes. But in an open-ended task, like deep research,
What happens then?
in deep research, it finishes building its concepts at just 28% depth.
That is a massive operational difference.
It highlights that different architectural designs literally dictate how a model thinks. Dense models finalize concepts early and require agonizingly long refinement phases, while sparse expert models can sustain much deeper, extended reasoning and construction before they finally need to stabilize their outputs.
Okay, we've covered incredible ground today. We've talked about layer-skipping lobotomies, the math of yanking the steering wheel with residual cosine similarity, and the deep proofreading of the logit lens.
We really went deep.
We did. But let's bring this all back to you, the listener, and the tools you are using right now. What does this mechanistic deep dive actually mean for your daily life?
Honestly, it changes how you should view the AI's thought process.
How so?
When you ask an AI to act as an agent, when you ask it to plan a marketing campaign, write a program, catch an error, and try again,
Yeah.
you are fundamentally shifting it from a static retrieval tool into a dynamic reasoning engine.
You are forcing it to physically mobilize its deepest layers.
Absolutely.
You're forcing it to constantly recalibrate, to unpack and repack its internal context, and to endure massive structural cognitive load.
And practically speaking, this tells us exactly why we should value patience.
Patience.
Yeah, in the tech industry, there is an obsession with speed. We want instant, sub-second latency.
Everyone wants it right now.
Exactly. But this mechanistic proof shows us that when you see an AI system taking longer to think in an agentic workflow, that extra computation isn't wasted.
It isn't a glitch.
No, not at all.
It's actively navigating the complexity of your task.
Yeah.
It is structurally mobilizing those deep 80th floor layers to suppress its own errors, reorient its goals, and fine-tune its output syntax so that the tool it's trying to use actually works.
It's doing the grueling iterative work so you don't have to.
That's a reassuring realization. The architecture of these massive models might seem wildly inefficient for simple trivia, but this paper proves they are perfectly primed for the heavy lifting of sequential autonomous planning.
It really is incredible to finally have that mapped out.
But as always, answering one profound question just opens the door to another.
Always does.
We've just seen that as a task gets longer and harder, the AI dynamically mobilizes deeper and deeper layers of its network to cope with the context and the required corrections.
Right. It eventually utilizes the full skyscraper.
It utilizes everything it has available. But an AI's depth is physically fixed by its architecture. There are only so many layers built into the model.
Right. It is not infinite.
Exactly. So I want to leave you, our listener, with a final thought to mull over today. We know it uses more depth as the trajectory gets longer.
Yeah.
So what happens to an autonomous agent when a task becomes so impossibly complex and the trajectory so long that it simply runs out of depth?
Wow.
What does that systemic failure look like, and how do we build the next generation to survive it?
That question is exactly what the frontier of agentic design is trying to solve right now.
It's a wild frontier. Thank you for joining us as we unpack the X-rays of the AI mind. Until next time, keep questioning the depth of the answers you receive.